standards, I guess, for what they want us to cover in A and B. So now they're pulling stuff that was in C into B, so they cut out a lot from B. So it's moving a little bit faster than last quarter, and it's in the summer too, so it's twice as fast.
Seriously.
So
that's crazy.
A lot of...
It's OChem too, so that's
yeah.
like, it's like a triple.
Yeah. This is my summer. It's okay.
There you go. Okay. Do you want to start from the beginning, or?
Sure.
Okay. For compounds 1 and 2, answer the questions given below the structures. Okay. Okay. For HNMR spectra, proton NMR spectra, assume that hydrogens in different environments will exhibit different coupling constants when they couple with hydrogens in a third environment. Okay. Assume that all spectra data are obtained at room temperature and the samples contain traces of acid or base impurities. Assume that any allylic or geminal couplings would be observable. Okay. Excuse me. How many hydrogen environments are there in number 1? Okay. So you have to think about. Have you talked about an enantiotopic, diastereotopic, something like that?
Like enantiomers and diastereomers?
Yes.
Mm-hmm.
Okay. So there's 2 ways to do this problem. Let me show you one way. One way is to just, let me draw it in here so you can see. Are you allowed a modeling kit on these tests?
Mm-mm.
Okay. Just wondering. Some teachers let you.
So the 2 on the sides are in the same environment.
Exactly.
Like the 2 back ones.
So let's call this A. So this would be A, and so would this. You're exactly right.
And then the top 2 are different from those 2 and from each other.
Very good. You got it. All right.
So B.
So it's like
3.
B and C. Very good. Never mind. You got it.
Okay.
So let's do the next one. B, this is HA. So let's see. How many hydrogen environments are there in number 2? Okay, so let's see. So B is definitely 1, right? This CH3 is also 1 by itself, but all 3 hydrogens are going to be the same. So it's 1, 2 so far. Let's take this and this one. So, well, they're both on OHs, okay? But technically they are in different chemical environments. So I think those are 2 more. Now let's take these last 2 here. That's what I was kind of talking about with, well, let me back up. What do you think?
Well, there's no like super electronegative things in the molecule. So I know if it was like a BR or something, they would be different, but I don't know what I would think if it was an OH.
Here's how you can tell. So, like, make this one like Cl or any other atom.
Mm-hmm.
Let's call it atom A. Or atom whatever. It doesn't matter.
Mm-hmm.
Make it like a Cl. Okay. Is this carbon chiral? Now.
Is it, okay, I get confused. Is achiral when it's like there's a stereocenter, or
Well, is there a stereocenter? Is what I meant to say. Yeah. Does this carbon have 4 different groups? in it?
yeah?
Yes, it does.
Okay.
And if I switch these, still
Mm-hmm.
chiral, which means those are actually enantiomers of each other. So if you replace one of the hydrogens with a chlorine and you switch these two on the same carbon and they're enantiomers of each other, those are called enantiotopic, which means they do not give the same signal.
Okay.
Okay, so that's a quick check. And let's go over why that is. That's weird. What? No. Don't close. Okay. Oh, sorry.
Good. So they're different because they're on different faces compared to the OH.
Right.
Okay.
So, at any given time, one hydrogen is going to be a different distance to the other things in the molecule as the other one.
Okay.
So, I don't know what's going on with this thing. Let's close all more things. No, I want to keep that open. Why? Let's try one more time. Okay. Sorry about that. Okay.
Yeah.
Okay. What is the coupling pattern that would be observed for the hydrogens in environment HA? Okay, so we need to find the hydrogens 1 carbon over, right?
Mm-hmm.
So it would couple with this,
Mm-hmm.
okay? It would also couple with this, and then, but because these are different, it's going to couple differently with these two. So it's going to be split like 1, 2, 3 times.
Okay.
So, go ahead.
So would that be treated then? It's like a doublet of doublets.
It would be, let's just go this way. This would be a doublet.
Yeah.
And then this would split that 2 more times. So you can either say it's a doublet of triplets.
Even though they're in different environments up top.
Let's draw it.
Okay.
Let's draw it. So let's assume this one over here splits it once.
Mm-hmm.
So then that's going to be split like this. And then these two are different environments. So let's say one splits it big, or let's say one splits it kind of small. That would be a doublet of doublets, but then the other one's going to split it also. And it's not the same exact hydrogen, so it's going to split it a different amount.
Mm-hmm.
So a doublet of quartets? Yeah, that's what I would say.
Okay.
Okay. Number 2. What is the coupling pattern in Oh, this hydrogen A.
Mm-hmm.
Okay. So let's see. So it's going to be the one next door.
And it only couples like to itself when it's a double bond, right? Like the geminal coupling.
Yes, exactly. So you don't have to worry about that one.
Okay.
So I would say HB, and I don't think you have to worry about.
This.
I think that's called
it's
long.
Too far away.
Yes, it's called long range, but I don't think that's going to affect it. So yeah, this one, and then I think they give you a hint in this. It says hydrogens in different environments. Okay, assume that the spectral data obtained at room temperature and samples contain traces of acid or base impurities. Okay, so I don't think this hydrogen on OH is coupled with this one, and it's because they're kind of taken on and off like so quickly at room temperature that it's not there long enough to couple with it. Have we talked about that before?
I remember him talking about like it's a hint if it says there's impurities in it or something. I don't remember exactly what he said, but that sounds familiar.
I think that's what he's talking about. Like with OHs at room temperature, you don't have to worry about the hydrogens coupling with these. Maybe. Let's just verify that.
Don't remember.
Let me see what it says. Like 99%.
Oh yeah, okay. So it says if the sample is very pure, there will be OH coupling. If traces of acid or base impurity, you won't see coupling.
That's
OH.
yeah, okay. That's what I thought. I just wanted to make sure. Yeah. So, okay. So then it should only couple once. So you should just see a doublet. That's it. Okay. What's the coupling pattern hydrogen B? Let's do this one first. So in this case, it'll couple with this and with that. So you're just going to see a doublet of doublets, right? Because it's different environments. Actually, no. Each of those hydrogens is exactly the same. So it's just going to be a triplet. Sorry, does that make sense?
Yeah.
Okay. So yeah, both those hydrogens in the same environment, so it's just going to be a triplet. And then in number 2, hydrogen B will couple with all 3 of those. So and all of those 3 are in the same environment, so this should be a quartet so far. Not with that one, but yes with this one and that one. Oh my gosh. And each of those are in a different environment. So take that quartet and split it 2 more times. So a triplet of quartets. Oh my gosh. So take a quartet. Split it 2 different times. So 1. 2. Yeah, triplet of quartets is the best I can think of. Does that make any sense?
Yeah.
Okay. For each compound, how many triplets will be observed in the proton-coupled carbon-13 NMR? Ignore small 2-bond couplings. Okay. Do you know what they mean by this?
I know there's 2 different carbon NMR spectrums.
One is proton coupled, one is proton decoupled. So, okay. So ignore small 2-bond couplings. Okay. I'm pretty sure they mean So, but let's take a step back. We're talking about the carbons in this case.
Mm-hmm.
So, so in that case, we're looking at what type of carbons they have. So let's look at this one. In this case, there are only two types of carbons, right? There's this one, which is the same as that one, and there's that one. The triplet, I think, comes from how many hydrogens attached to. So let me make sure that's right. Proton coupled. I don't think I have proton coupled in here. I only have proton decoupled. My book only talks about decoupled. Let's see if this one talks about coupled. I'm pretty sure they mean carbons with two hydrogens on them, like CH2s.
That's decoupling.
That's decoupling, but do they talk about proton coupled? Oh, that's it. I was right. Okay. It just means it's coupled to, it's coupled to all the hydrogens it's attached to. So, so like this, I was right. I should have just said it wasn't, but I just wanted to make sure. So proton coupled NMR means every hydrogen it's attached to will split it. So split it once, split it twice. So that would be a triplet. Okay. And then this is just split the once. And that's what they're talking about right here, actually.
Oh, okay, because the decoupled is no splitting, right?
Right, it's just
all
single peaks.
Okay.
Yeah. So let's do something like this one, where it says this blue carbon here. It says the C is coupled to two attached hydrogens, so it makes a triplet basically. Okay. Now, that two bond that they're talking about. They're saying ignore small two-bond couplings. What that means is like long range. So it's coupled to these ones attached to it, but like farther away, it can couple a little bit to these. You see how it splits it a tiny bit? Okay, so it's just saying ignore those. So you're just doing the ones attached to it. So you're going to see one triplet in carbon in molecule 1, and you're going to see one triplet in molecule 2.
Okay.
Why will one not undergo a double dehydrohalogenation to form an alkyne? Okay. So that's not an NMR question. Okay. So let's think about what they're talking about. What they're talking about is using a strong base like NaNH2. To come in, take a hydrogen off as a leaving group leaves. It's basically an E2 type reaction. But there's a problem with that. Is how are we going to make a triple bond between these two carbons and still have this triangle thing in there? So it's this cyclopropane thing that's getting in the way.
Mm-hmm.
Usually when this reacts, it reacts like this.
So like a normal chain molecule, not a cyclic molecule.
Right. There's going to be so number one, that's too many bonds
Mm-hmm.
on the carbon to, because if you try to do a triple bond here, that's like way too many bonds on that. Even though the bromines leave. That's 5 bonds on each of those carbons. Not to mention the angle strain and also so this is not going to happen. In this case, it could happen. This could come in. This flips down. That leaves. That forms the double bond.
Mm-hmm. And you do it again to get rid of the other bromine, right?
Exactly. You got it. So I would say something like, because of this ring, that ring won't break. Let's see what else. Forming too many bonds, so we can't form a triple bond.
Mm-hmm.
Take your pick.
Okay.
Give an example of a compound that, under treatment of excess base, will undergo a double dehydrohalogenation. Oh, okay, so something like this, but we need to form
So
3.
I'll say to skip that one.
Okay, just kidding.
We're not doing any like alkyne addition other than with hydrogen.
Oh, okay. How would you prepare a racemic compound of 2 from propane in a multi-step synthesis? You need to show mechanisms, show how all necessary reagents, solvents, etc. Now, before we go any further, there's 2 OHs on here, so that's what we talked about earlier. There's
And
only
there's sin.
and there's sin, exactly.
Okay.
So that's a good hint.
So that was the second one we did.
The OSO4
Mm-hmm.
one. So let's do a retrosynthesis. Let's go backwards.
Mm-hmm.
Let's go back to the double bond, which was like this. With CH3 and an H and an H and an H. Does that make sense?
Mm-hmm.
And then, then we know how to go from here to here. That's the OSO4, NaHSO3, okay. But then we got to think about, how do we make a double bond? How do we make, because we want to start with propane. We want to start with this. Just regular propane.
Mm-hmm.
Okay. So we get from here to here, but how do you usually make a double bond? What kind of reactions make double bonds?
The carbocation.
Yes, that was E1, right? Or something like
Oh.
this, which is E2.
Mm-hmm.
So the kind of the reactions that make double bonds are eliminations.
Mm-hmm.
So we're going to do an E1 or an E2. So, which means before we can do any eliminations, though, we need to put a leaving group on this. There is no leaving group on it.
Mm-hmm.
So let's talk about putting a leaving group on this. Okay? Now, have you talked about radical reactions? Like, not like awesome reactions, but like this. Like Br2 and light? Or Br2 and heat?
Yes, I think so.
I'll give you a hint. Whenever you have an alkane, this is the only thing you can do to it. This is the only reaction that you can react this with. So what happens is, when you use this, it replaces an H with a halogen.
Mm-hmm.
If you use bromine, bromine is very selective. Bromine only wants to replace something that forms the more stable radical. So secondary versus primary. So, do you want to go through the mechanism on this, or it's kind of a long mechanism?
It's okay.
Okay. So, this is going to replace an H with a Br. Now, and the reason I know it's going to be this is because this would form the most stable radical as secondary. Mm-hmm. So it's going to do this. Does that make any sense?
Mm-hmm.
Okay. So you replace an H with a Br.
Mm-hmm.
Now we have a leaving group. Now we have a secondary with a good leaving group. We can use a strong base to do the elimination.
Mm-hmm.
You could do an E1 elimination, but here's the problem with E1. Never choose E1 because you're going to also get SN1. It's not what we want.
Okay.
So use E2 in these synthesis problems. So let's use a strong base. Use a strong base that's not so great as being a nucleophile because you don't want SN2.
Mm-hmm.
So let's use a big and bulky base. Let's use this. T-butoxide.
Mm-hmm.
I don't know how you abbreviate it, so I'm just going to draw it. Sometimes it's abbreviated like KOTU, TBU. Sometimes it's like, whatever. But that's a big and bulky, strong base. And that's it. So it helps if you go backwards.
Mm-hmm.
Like, oh, I gotta put 2 OHs on. Okay, I know how to do that. And it's a syn addition like you said. It's this one. Well, I started with this. How am I going to get a double bond? Well, I can do elimination, but I need a leaving group.
Mm-hmm.
So this is the way, whenever you have an alkane to put a leaving group on, this is the way to do it. Okay. Okay. Oh, by the way, we should have shown one more thing. When this adds on, it could have added on the top, or it could have added on the bottom.
Okay.
If it did the other way, right, you'd get the other enantiomer of this.
Mm-hmm.
So that's what they mean racemic. They show
Yeah.
the racemic. So you have to. I think they want you to show both. They want you to show like the other enantiomer of this. Does that make sense?
Yep.
Okay. Give a detailed mechanism for each reaction used in the synthesis reaction below. Use curved arrow notation to show the movement of electrons and draw the structure of each intermediate, clearly showing stereochemistry. All right. It's a good one. It's one of my favorites. And you said you're good with this one. You've seen this one before.
Mm-hmm.
Okay. Do you want me to go to the mechanism, or you want me to just skip along?
Sure. You can skip it.
Okay. So just kind of. Oops, actually go the other way. Go to this step here.
Mm-hmm.
Okay, but I do want to go over one thing with you.
Mm-hmm.
Okay. And that is, what happens next here? So, yes. So, we made it clearly showing stereochemistry. Okay. So we know this is a good nucleophile, and if we don't use anything else in step 1, just this, we have to put this on as the nucleophile. Now it does have to come in the back, right? So that's why you've seen this before. So it's a backside attack. The bromine here is coming towards me, so this Br- has to be going away from me. So it's going to end up as an anti. The bromine's going opposite ways. So let's do this. Now, but we have to think about one more thing. We have to end up with a double bond across this somehow. So and we can do that as long as there's a hydrogen to take off still. So what I mean by that is this. Let's think about where the bromine's going to add on. I don't think it actually matters because they don't show you the dashes and wedges here anyway. So, all right, let's just put it on somewhere. Let's put it on maybe here, and this breaks off. Honestly, it'd actually do the other one. Just kidding. It should actually do the other one because this positive can kind of be more likely to be shared there, but I don't think that's beyond the scope. So let's just choose one. So now we have this. I'm going to turn the air conditioning back on. I think someone turned it off. It's super hot here. So then, when this breaks off, it's still coming towards me. So that's Br. Now, you have to be careful here because you have to watch out for stereochemistry. So, I'm going to show you something that happens with SN2 type reactions. Okay? And this is kind of how this is. It comes in the back as the leaving group pops towards the front. So let's say it looks like this. So if this was the nucleophile, the Br minus. Once it comes in here and this breaks off, the problem is this carbon here is not a tetrahedral. So it has to kind of like umbrella. You ever, like in a storm, like it's when you have your umbrella and it like flips up? Same thing here. Like this thing flips up like an umbrella. And you see how the chlorine end up coming the other way? So it's going to end up looking like this. So you have to track this through the whole mechanism. Okay, last step is step 2, which is use a strong base to make a double bond. Well, there's still this, right? So the NaNH2 can come in, take that hydrogen off, as this bond flips to a double bond, as this leaves. And we're done. Okay. Compound theory molecular formula C5H8 exhibits 2 3-proton resonances and 1 2-proton resonance in the H NMR spectrum. 3 is converted to compound 4 upon treatment with sodium and okay. So there's a hint for you. So compound 3 with the formula C5H8. Have you gone over something called the degree of unsaturation or okay. That's probably, if they want you to draw it from this, that's going to give us a hint. So 2 times 5 is 10, minus 8 is 2, and then plus 2 all over 2. So you get 2. So 2 degrees of unsaturation. So it either has a ring and a pi bond or 2 pi bonds. But here's the hint. Once you treat it with sodium and NH3, thank you. It forms another compound. So we use this to treat triple bonds. And this is a special type of hydrogenation. This kind of hydrogenation turns triple bonds into double bonds that are trans. Okay. So all these are pointing to I need a triple bond in my first molecule because that triple bond has 2 pi bonds. Okay. Now let's see if we can figure out what the proton resonance is. So, okay. So let's see. If it looked like, so it's 5. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, so that's one possibility. The other possibility would be 1, 2, 3, 4, 5. If I had it here, it'd be the same. So I think there's only 2 possibilities, right? Because then 1 carbon and 2 carbons on this side, or 1, 2, 3 carbons. Yeah, I think that's it. So let's see which one it is. It says exhibits 2 3-proton resonances. Okay. Oh, well, it's probably this one.
Yeah, because it has to be where there's 2 CH3s.
Exactly.
Okay.
So this is probably what we started with. And it exhibits 1 2-proton. How are you doing so far?
Good.
Okay. All right. Well, so let's go to here then. So there's 3 ways to hydrogenate. There's using Lindlar's catalyst, which stops at the alkene cis. There's this, which stops at the alkene trans. Or using hydrogen and some sort of metal catalyst, which goes all the way down to the alkene. Okay. Okay. So let's do this one though. This goes all the way to the goes to the alkene, but it's going to end up being trans. So 1, 2, 3, 4, 5. 1, 2, 3. Okay, so this is compound 3. This is compound 4. And then it says if you treat compound 3 with H2 and Lindlar, what does that do?
It stops at the alkene, but it's cis.
Very good, exactly. So that's compound 5. Okay, both 4 and 5 undergo reaction with ozone. Okay. Whenever you see ozone, ozone cuts this exactly down and adds oxygens across that. Have you seen this before? Okay. Let's talk about ozonolysis.
Oh, he cut that out now for this. Like, he didn't update the practice midterm before, but he took that out. We're not doing that.
Never mind, just kidding.
Oh, okay.
Alright, so then let's skip that one then. and then show the structures. Okay, so I guess it's going to be something else then.
Okay.
Are any of the compounds 4 through 7? Well, we only have 4 and 5 because they're only 6 and 7. But are they chiral? No, I don't see anything that's chiral here. These are diastereomers of each other, cis and trans, but that's pretty much it. Okay. Moving on. Okay, which of the following reactions give the structure of the product? Assume all chiral starting compounds are optically pure. The product exists as a racemic mixture. Put an X in the box. Show stereochemistry clearly. And write no reaction if there's no reaction. Okay. What do you think?
So that is going to add on OHs that are cis.
Very good. So here are the products. Here's where you gotta be careful, because those OHs could both attach on the top, or they can both attach on the bottom.
So it's racemic.
Exactly. If it exists as a racemic mixture, do you have to draw both, or can you just put an X?
You can just put an X.
Okay.
And normally he just, like, if we don't have the X, you would just do like plus enantiomer.
Oh, okay. Gotcha. Alright, on to the next one.
Getting rid of the double bond.
Yes. Hate is going to hate, acid is going to propane, right? So this is going to be H3O plus. Where's the H go, and where does the plus go?
The plus will go on the side of the ethyl, and then the H will go there.
Exactly. That's the first step. Now,
And
stop here, right? Whenever you make a carbocation, look left, look right, look all around, see if it's more stable somewhere else.
it's the most stable there.
Yeah, it's fine. It's fine where it is. So we don't have to rearrange anything. And then water's going to come in. That's the only other thing we have that could be a nucleophile. But let's think about stereochemistry before we do that. What's the shape of this carbon?
Planar.
Yeah. So when the water comes in, it can come in through the top or the bottom. So just like SN1. So it can come in through the top or it can come in through the bottom. So yes, we are going to get a mixture here because that will be a chiral carbon. So what you end up getting is 2, 3, 4. One of them like this, and one of them like that. Oh, that's not right. 1, 2, 3, 4. Yeah, it's right. I mean, I drew it the wrong way, but it's still the right answer. Sorry. Second carbon over, second carbon over. But you get the idea. Yeah.
So that one is racemic.
It's going to be racemic, exactly.
Okay.
Does that make sense why? Okay. Potassium ethoxide. So there's a few things we need to know about ethoxide. It's a what and a what?
Bulky base.
What's a strong base?
Mhm.
Definitely anything O minus. Ethoxide's kind of not too bulky. It's the T-butoxide that we have to worry about.
Yeah.
That guy is big.
Mhm.
So strong base is also a good nucleophile because it's negatively charged. But they give you a hint here in heat. Heat always favors elimination.
And that is E2?
Yes, very good. Okay. There's also another hint. Look at where the leaving group is. That's a secondary.
Mhm.
So once again, it's going to be a little bit hard to do SN2, even though it's a good
Mhm.
nucleophile. So the heat is the hint, though.
Okay.
Okay, so let's do an elimination. Now, here's where you got to be careful. So I did E2 like the generals, but now we have to do the specifics. Before an elimination can happen, you have to have a leaving group and a hydrogen that are anti-coplanar.
Mhm.
Or do you guys call it anti-periplanar? Which one?
Anti-coplanar.
Okay, so yeah, so we have to twist this molecule until the hydrogen that's going to be taken off and the bromine are going opposite directions.
Okay.
So let's twist it this way, like that.
Mhm.
So put the hydrogen down here. So that's going to be hydrogen here. You did that on purpose, so you would have to twist it. So the leaving group here and the hydrogen next door have to be anti-coplanar, and they are in this case. So now all I have to do, you don't have to do the mechanism, you just go right to the product. Basically take this off and take that off and draw the double bond, but lock it into place exactly how it is right now. So this methyl should be coming towards me, this hydrogen should be coming towards me, that methyl away, that ethyl away. So it should look like this. Does that make sense?
Mhm.
And that's why that was the purpose of this problem.
Okay.
So you can lock everything in its correct position. Okay, what do you think? Protonate. That's all we can do, right?
Mhm.
And the only thing we can protonate is this. So let's protonate. I'm going to protonate it here. I know you're thinking, well, how do you know they're both secondary?
Oh, with the last one, would it be it's not a racemic mixture,
No,
right? Okay.
it's just one answer, one product.
Okay.
Okay. In this case, I'm going to protonate this one and leave that one positive.
Mhm.
And here's the reason. Because I can shift it then to make a
Mhm.
more stable carbon-cation. So this can shift over. You get this. These are all the hydrogens because we don't have a nucleophile,
Mhm.
right? All we said, this is a little bit of catalytic H+, so we can't use any nucleophiles here. So what do we have to do next then? If we can't put anything on, right, to that positive,
Do you take off the CH3 group? Or?
take off something,
Okay.
right? Which means just like E1. In an E1 reaction, something comes in and takes off an H, and then this flips down to a double bond.
Mhm.
So that H that was put on is going to be taken back off. And that's what a catalyst does. It regenerates itself,
Mhm.
right? So now we have three choices. We can make a double bond here by taking this one off and flipping that double bond down.
Mhm.
We can make a double bond there, which is the same thing, or here. Now, I don't know if your teacher wants you to just do the major product or the minor. Doesn't really say. But I'm just going to show you the major product.
Okay.
Is that the answer, T?
Yeah.
Okay, major product. Just
Okay.
yeah. The major product is the double bond with the most carbons around it.
Mm-hmm.
Okay, so which is either going to be this one here or that one there. Either way.
Okay.
So that's how you know it's going to be that way. Well, they're the same exact thing.
Mm-hmm.
Just flipped around. Does that make any sense?
Yeah. So you're just like shifting around the double bond to where it's more stable.
Exactly.
Okay.
Exactly right. It always reminds me of meow.
Yeah.
Or when they write it like this. Like, homie. Okay. If it just said BR2, we would add the two BRs anti to each other. But this is the nucleophile that comes in instead of the BR minus.
Okay, so it's only one BR and
Exactly.
OH.
Mm-hmm.
Okay. Are they still anti?
They are anti, but once again, we have to know where this adds on.
Okay.
It's kind of like we talked about where that positive gets shared.
Mm-hmm.
Let me just show you.
Okay.
First thing is we're going to get this. And you've seen that mechanism, so I can kind of skip it.
Mm-hmm.
These are wedges. I'm very messy writing. I apologize. So the methanol is going to come in. But to which carbon?
Is this anti-Markov or
Well,
does it not really matter?
it's kind of Markov-Nikov if
Okay.
you think of it that way.
The carbon with the methyl on it?
Yes, it is. That positive can be shared by that tertiary carbon.
Mm-hmm.
So this is more attracted to that one.
And then it breaks off.
And then it breaks off. And this CH3 in the back kind of umbrellas towards the front.
Mm-hmm.
So you get and once something else comes and takes the other H off, you get this. And this CH3 is this CH3 right here. And that should be a dash.
For this one, it could be racemic because the BR could have formed in the back.
Very good.
Okay.
Mm-hmm. Skipping that one. And the next one. I don't think we ever went over this mechanism or I think we just talked about it as an anti-Markov couple.
Mm-hmm.
Forgot to tell you that it's also syn addition.
Okay.
So it's because when the B and the H add on, they add on the same side at the same time. So what you're going to end up getting is an H and OH anti-Markov syn addition.
Mm-hmm.
So just by knowing that, you can predict the product. So let's assume it comes on the bottom.
Mm-hmm.
Oh, well, they're both the same carbon. They're both. I guess it really doesn't matter which one we put it on. So anti-Markov doesn't matter, but the syn addition does matter. So let's put it maybe OH here,
Mm-hmm.
and the H there. But you're also going to get the other one,
Mm-hmm.
and you're also going to get on the top, but you're also going to get the other one on top too.
Okay.
So you're going to get a whole bunch of mixtures of this. So every single one possible. So this one, I guess you would get a racemic mixture then. Yeah. Does that make any sense?
Mm-hmm. So is that an epoxide?
Yes, forms an epoxide. Once again, it's going to go either one side or the other side. It's either 50-50. Just kind of like the bromine thing. Same idea.
And this is still part of forming the epoxide, right?
This is breaking it open.
Oh, okay.
So forming it, breaking it open.
Okay.
So let's assume it came on the top. Oops. So there's your epoxide. Now, it's acid catalyzed, so that's the first thing that happens is it's going to get protonated. And which side is the water going to come in?
Do you mean like top or bottom, or what side of the?
Which carbon, I should say. And which side?
The left.
The left, and it comes in on the
Back.
Yeah.
Oh, okay.
The bottom.
Yeah.
Yeah, so this is on top, it'll come in on the bottom.
Okay.
Exactly. So what we end up getting is this. The water that came in on the bottom is going to end up here. This one breaks off on the top, so it goes here. Once again, that's if the epoxide was formed on the top.
It could be on the bottom.
It could be on the bottom too. So, and then you'll just get the reverse of this, which should, once again, is going to be, most of these are racemic.
Yeah.
That's what I noticed.
I'm going to probably, if I don't know, just put that it's racemic, because chances are it probably is.
Yeah, chances are, I guess, yeah. Have you seen D2 before?
Yeah, so it's like just H2.
Very good. It's the same exact thing. This is just a metal catalyst. That's all you need to think of. So it's just going to hydrogenate. But here's what you have to know about this. This is a syn addition. This is another one of those syn additions. So I think there's 3 altogether. Hydrogenation, this, hydroboration, and the OSO4. Those are all syn addition. When I mean hydrogenation, I mean like this, not the other ones we talked about. Just H2 and a catalyst, that kind of hydrogenation.
What was the other one? You said hydrogenation, OSO4, and...
This, hydroboration.
Oh, hydroboration.
Yeah. Hydroboration oxidation, to be specific. And that was the point of this one. So when you put the H's on, make sure you put them like both going the same direction. So, or sorry, when you put the D's on. Sorry. So let's show that.
The weird structures always throw me off, even though I know it's like the same thing. I never know what to do with them.
I know. So basically ignore everything else except for the double bond. So there are 2 possibilities. One possibility is they're both going, if they attach onto the front of the double bond, the top I should say. And the other one would be them going kind of straight down in these positions right here. So one of them is this, the other one is switch the H and the D's basically. Let's see. Have you seen LDA before?
Yes.
It's a strong, big, and bulky base. I probably should have added it to your list over there. I'm sorry, but it's another type of big and bulky base, but it's a strong base.
Mm-hmm.
It stands for lithium diisopropyl amide. Yeah, so it's like this.
Mm-hmm. Yeah.
Okay, and lithium. Okay. So it's not going to be used as a nucleophile. We hardly ever use it. It's just too big.
Mm-hmm.
It's used as a strong base. So
E2.
it's going to be an E2. Very good. So let's think about what can happen in this case. Here's the leaving group.
Mm-hmm.
I take hydrogen off on the next carbon over. So it's the base is going to come in, take that one off. This is going to flip down and that's going to leave. It all happens at once.
Mm-hmm.
And you end up getting a triple bond. Does that make sense?
Mm-hmm.
How long do you want to stay? Because it's already...
It's been 2 hours.
It's up to you. You can finish the test or...
I'll just finish the test.
Might as well. Alright.
Let's just do it.
Okay. Shown below is the HNMR spectrum for a compound for the molecular formula something, C4 something. What does that say?
Oh.
Is it on the key maybe?
Yeah.
Sorry.
Okay. My printer's weird sometimes. It just cuts stuff off.
Let's see how we did. Oh, I forgot to tell you something. Darn it. I'm glad we looked at the key. Okay. Here's you got to be careful.
Oh, the H can go away.
Yes.
Okay.
If you're using a strong base, it's going to keep reacting and take that H off.
Okay, yeah.
Sorry, I should have showed you that earlier.
Okay. I remember that from lecture.
See how we did otherwise. Good. Did good. Yep.
Mm-hmm.
Oh, we skipped a page. Or did we?
Mm-hmm.
Did we skip a page? No. This key is different than... Yeah, this is different than... Oh, skip this one. Okay, never mind.
Okay.
Sorry. I just want to see how we did. Okay. We got all that stuff right. It says C4H8O. Okay. So let's see the problem now. Okay. How many degrees of unsaturation are there for this molecule? That's just the formula.
Mm-hmm.
Do you know the formula?
Yeah, it's 2 times the carbon plus 2 minus the hydrogens, and there's nothing else, and then over 2.
Right, exactly. You got it.
So, 1.
How many different hydrogens environments are there for this molecule? Okay, let's see. That's 1.
Mm-hmm.
That's 2. I think these are separate, so 3, 4. 1, 2, because they're not symmetric either.
Mm-hmm.
So yeah, so 1, 2, 3, 4. Looks like 5. Alright, so if you have a degree of saturation, one either you have a ring or a pi bond, one or the other. So let's see. I doubt that we have a ring because we have a CH3 here. Let's try some chains. So 1, 2, 3. Go ahead.
It doesn't look like there's an OH because it's usually like a broad singlet. I think, 'cause
Yes, and that's usually in the range of between 3 and 5. And you're right, it's a singlet and it's broad. You're exactly right. Yep, so that must mean either one or two things. Either it's some sort of ether, or yeah, some sort of like double bond oxygen, like an aldehyde or a ketone. You're exactly right. So we have a couple things to kind of work out. Let's see. Let's try this one. we would see this hydrogen, but it would be way over here at like 10 or 11. Aldehyde hydrogens are way over here, and that's not what we see. Okay. Let's try this one. In this case, we should see 1, 2, 3. We should see 2 different CH3s. Nope. So that's out. Let's try something else. We only have one CH3, CH2, CH2. So there must be some branching maybe. So like CH3, CH2. That's way too many. Let's see. What if we had one hydrogen?
So would those be CHs by double bond probably?
Yes, that makes sense. And that would take care of the double bond, but not the oxygen. Let's see. Now let's just look at the splitting too. 3 hydrogens, and it's a triplet, so it must have 2 next door neighbors. So I'm guessing these two kind of go together. So it must be like a CH3, CH2. So like this, like a CH3 and a CH2. Okay. And that takes care of the CH, and there's only one more H. In fact, this actually, it was around 6 or 7. I guess it could be this.
And he gives us the chemical shifts too. We didn't have to memorize them. There's a thing in the back that he
okay. Yeah, so let me see if this makes sense. This one is 1, 2, 3, 4 peaks, so it should have 3 neighbors. 1, 2, 3 neighbors. Or it could be this. These would only have 3 neighbors, and these would only have 2 neighbors because of the O here. Let's check our chemical shifts. Uh, 6 to 7. Alkene. Alcohol would be 3 to 4. So maybe one of these was, but it doesn't make sense why it should be like a singlet. Unless it's really cold and it can couple and it's really pure. So then I guess it could couple. So so I guess this could be that last one hydrogen. It has 1, 2, 3, 4 things it's peaking, coupling to. So in that case, yeah, but why would we miss something here maybe? Hold on. Yeah, aldehydes are 10, so it's not an aldehyde. If it was a ketone, it would have to have 1, 2, 3, and 1, 2, 3. Yeah, that's not going to work. Alright, so this is it. This is the only thing we have. And then from here, that would take care of these 2. Or maybe not. Maybe this one hydrogen here is just this one hydrogen here. and these two are somewhere else. No, that doesn't make any sense either. The only thing I can think of this is my best guess, I think. Because this hydrogen is close to double bond but also close to the O.
So that could be the farthest
That
one.
might be the farthest one, yeah. And then these two hydrogens here are going to be these two hydrogens very close to each other. And then this CH2 here, it's a quartet from these three neighbors there. And then this is a triplet, so it must have two neighbors here.
Okay.
This is my best guess, I think. So let's see. Yay! Okay. Okay. How many carbon resonances are expected in the carbon-13 NMR spectrum? So how many different types of carbons are there, basically?
4.
There's 4, yeah. Label which one is which. We kind of did that already. So like this one would be A. For B and C, I would say probably this one's B. And this one's C. Only because...
Closer.
Yeah. And then this should be the other two. Is that it?
Yep.
Dang.
Alright. Okay. So there's one more chapter on the test, chapter 14, but I feel pretty good about all that stuff's about.
You sure?
Makes me feel better about it. Yeah.
Okay. Do you want to go over chapter 14 or not? Or are you good on it?
We didn't do a ton in chapter 14. Mainly, it's delocalized pi system. I don't have any specific questions about it, but if there's any like main things you think I should know about it.
It's mostly, a lot of it has to do with resonance, it looks like. And then the more conjugated, the more stable.
And conjugated is when it's like every other, right? Or
Yes, exactly. So even something like this can be considered conjugated.
Okay.
Right? Because it's like double, single, double. Anyways. Do you want to go over NBS and allylic bromination? Here's what you need to know about that. Don't worry about the mechanism so much, because when you see NBS, it stands for N-bromosuccinimide, which means it just means that the bromine's going to switch for a hydrogen on the most stable carbon. And the allylic radical here is actually more stable than a regular secondary. So, like if I take this H off and make this a radical, that position is the most stable position out of this whole molecule. Okay, so that's where the bromine's going to go. It's the same thing as using Br2 in light or Br2 in heat, except for we know it's going to go on the most stable, which is the allylic position. That's all you need to know. So NBS switches it. Similar reactions. Okay. Let's talk about this reaction. So this is a secondary, right? Usually with a secondary, I wouldn't say, oh well, let's back up. Is water a good nucleophile?
Yeah.
Well, only
no.
it has to be negatively charged, right? Is it a strong base?
No.
No, it's neither, right? So it's going to have to wait around. It's going to have to wait around for this to leave.
Mm-hmm.
And then you get this. Is that okay?
No.
Well, what kind of radical is this? Or sorry, what kind of carbocation is that? Secondary, and also it's what? When you're one bond away from a double bond, that's called what position? Allylic.
Oh, okay.
That's the allylic position.
I never knew what he was talking about when he talked about allylic stuff, so that
that
makes sense.
That's what it means.
Okay.
Let me go over why that's important. Let me draw in the carbons and I'll show you what I'm talking about here. This secondary is not bad, but this is stabilized through resonance. This double bond can flip over here, and that puts the positive over here. So it can spread the positive charge out between the two carbons. And that's why allylic is so stable, is because it can spread that positive charge out. So allylic carbocations are, like, pushes them up in stability.
Okay.
Same thing with benzylic. Have we talked about benzylic also?
I haven't heard that, but that would make sense.
This is called a benzylic. It's one single bond away. It's kind of like the allylic, right?
Yeah.
One bond away from a double, but this case it's one bond away from here. It's even more stable because this can resonate here.
Keep moving around the whole thing.
Exactly. So it stabilizes it. That's what this is talking about.
Okay.
It's saying this first step is usually not great, but this is okay because that carbocation is stabilized. Now, the next thing that comes in has a choice. It could come in like this, because that double bond can resonate back and forth, or come in onto this one. Okay. Now, and that's what it's talking about.
Oh, I think it's like
Oh yeah, that's what it's talking about here. So you're going to get a mixture of the two, depending on where that carbocation is. Okay. Okay. Let's talk about this. Have you seen these before? All they are is good nucleophiles. They're not strong bases, but they're good nucleophiles. So what they're saying is, if you have these allylic bromides like this, it could still do a regular SN2. It can still come in here, and that can still be normal conditions. Okay. So it doesn't have to wait for that to come off. Let's see. Have we talked about Grignard reagents?
Yeah, a little bit.
Okay. So,
I don't really know what that means though, but I know the word.
Let's talk about it. Let's use this. A Grignard reagent, well, we make a Grignard reagent by adding magnesium and ether, and we heat it up basically. This is how we make a Grignard reagent, but let me show you what it's useful for. What happens is the magnesium inserts itself in between the bromine and this carbon right here. So you get this. So in between that dot where the carbon was and the bromine, there's magnesium now. Now let's see why that's important. What's the charge on magnesium?
That's 2.
Sorry. I was going to go to the periodic table, but you already moved +2. Yeah. What's the charge on bromine?
-1.
So something else must be negatively charged, right? And that's this carbon right here. This carbon gets a little bit of it gets that negative charge, which makes it a good nucleophile. That's the point of making these Grignard reagents, is so we can use this to attach onto something else. So that's what they're showing you here. Okay, talked about conjugated already. The more conjugated, the better. These are all types of conjugations. Not that one though. and not that one.
So they're too far away.
Exactly. Okay, let's go over this.
Okay.
Have you talked about 1.2 edition versus 1.4 edition? Let's go over that.
I remember this stuff from, I don't know the 1-2 name or whatever, but I remember talking about this in class.
Okay. So, let's start talking about this. Okay. Let's react this with HBr.
I
So-
know, sorry.
Go ahead.
The one that forms faster is going to be the major, even though it's not as stable.
It depends on the temperature.
If it's at lower temp, and then if it's at higher temp, it's the opposite.
Yes, exactly right.
Okay.
So let's go through both of those products. So first thing is we're going to protonate it, right? So it doesn't matter which one you protonate. Let's just protonate this one first. So H goes here and positive goes there. And once again, it's because that's a secondary allylic, which makes it a little more stable. Now, if the Br comes in now, that's the kinetic product, meaning the faster product, which you get this. If the carbocation rearranges first, if this flips over here, right, and you get this, you get this product. This is the thermodynamic product, which is the more stable product. Let's go over why it's the more stable product. Do you remember we talked about double bonds? They want to have the most carbons around them. So yeah, this is the most
internal one.
exactly. So at high temperatures, you're going to get the thermodynamic product. At low temperatures, you're going to get the kinetic product, which is the less stable. You're exactly right. Okay.
And we didn't do
Anything else in there?
7 through 11. I don't know if there's anything else.
That's pretty much
We
it.
took out the DL's alder and stuff.
The only other thing you might have to show is maybe these diagrams. I'm not too sure, but
Yeah, he spent a lot of time talking about like why the kinetic versus thermodynamic is favored.
okay, very good. So you're good on that. Any last minute questions before we wrap this up?
I think I'm good. I feel a lot better about my midterm, which is good.
Yeah, very good.
Yeah, I'm good. Thank you.
You're welcome.
So if I have a card, do I pay online or can I pay?
Oh, I have a
thing,
I have a
right?
swipe
Okay.
thing.
I couldn't remember. Sorry, so find the right card.
Thank you.
Thank you so much.
You're welcome. Feel free to text me or email me if you have any last minute questions.
Okay, thank you. I'll most likely be back a couple times before the final, so
Totally fine.
thank you so much.
Never really busy in the summer, so.
Okay, perfect.
Let's start with SN2. SN2 is a good opportunity to go over what a nucleophile is, what's a good nucleophile, how it comes in, and why it comes in. So let's talk about something like this. Most of organic chemistry is positive-negative attraction. Like negative things attract to positive and vice versa. So what happens is this bond between the carbon and the bromine is a polar bond, meaning you get a little bit of a positive on the carbon and a little bit of negative on the bromine because bromine is more electronegative. It's a polar bond. So that means if something negative were to come in, it would not want to go where the bromine is. In fact, it would be like repelled by the bromine, but it would be attracted by the carbon. So that's why, by the way, it goes around the other way. It's a backside attack. So when that happens, let's say here it is like this. Let's say Cl minus is my nucleophile. Okay. Good nucleophiles have negative charges. And the reason why is because now they are much more attracted to that partial positive. Weak nucleophiles have partial negative charges, like water. Water is a weak nucleophile. So that's because oxygen only has a partial negative charge. Alright, so then backside attack, this comes in as this leaves. Okay, so that's a basic SN2. It all happens at once. It's single step concern. Now, one more thing to note is SN2s are dictated by how many things here are going to block this nucleophile from coming in. Methyl's the best because there's nothing here blocking it. But the more blocking groups I have, like if it was a primary, now it's a little bit more blocked. If it was a secondary, even more blocked. And if there's a tertiary, tertiaries don't do SN2s because there's so many things here blocking. It's hard for the nucleophile to come in there. All right, let's talk about SN1. SN1 is a little bit different. In fact, SN1 happens when you don't have a strong enough nucleophile. So, like water.
And for this one, is it the opposite, that it prefers tertiary and then primary it's the least likely to do SN1?
Yes,
Okay.
exactly. Let's go over why. Water is not a good enough nucleophile to get in here. Also, it's too blocked to get in there, right? It's just too many groups like we talked about right here. So water is just going to sit around and wait. It's going to wait. And then eventually, this happens slowly, but eventually this bromine can pop off as Br minus, which is really soluble in water, by the way. So that's the first step. Okay, and water's like, ooh, now there's extra room for me because that bromine's gone. By the way, 1, 2, 3, that's trigonoplanar. It's flat. So it actually looks like this. Now, so that means when the water comes in, it can come in from the top or it can come in from the bottom 50-50. So when you think about stereochemistry, this one is an inversion of stereochemistry. Whenever the nucleophile comes in the opposite of the leaving group, it always inverts stereochemistry. Dashes to wedges, R to S. In this case, you're going to get a 50-50 mix of the water ending up here and ending up there. Does that make sense?
Yeah.
Okay.
So is the reason they do SN1 with that because it's like the most stable carbocation?
There's like 3 reasons for it. 1, you don't have a good nucleophile, so yeah, it kind of has to sit around and wait. 2, it's too blocked to do an SN2. And the third is, yes, it forms a more stable carbocation. Tertiary is more stable and secondary is more stable than primary. So all those support SN1.
Mm-hmm.
Okay. Do you want to talk about the solvents? Or you want to go on to the other mechanisms? Oh, we should probably finish this mechanism actually. Sorry. So once you've opened it up, and so you've done two things. You've opened it up, and you made it a full-on positive charge, which this partial negative charge is much more attracted to it now. So it's easier for it just to come right in.
And that just comes on as OH, right? Because it'll take one of the H's off.
Yeah, so it'll do this, and then another water comes in and takes the other H off. Yeah. And then, it's the last step.
So for SN2, it's bulky bases, right?
SN2, you want a good nucleophile.
Mm-hmm.
The best nucleophiles, do you want to go over how to tell if it's a good nucleophile or not? Or?
Sure.
For the most part, 99% of the time, if you see something that's negatively charged, well, actually, all good nucleophiles are negatively charged. But you have to watch out. Like you were saying, the size of the nucleophile can dictate how easy it is for it to get in here. So, if I have a really good small nucleophile, it should be relatively easy to get right in here.
Mm-hmm. This
is a primary, right? So primaries can do SN2 pretty easily. But if I have a big, bulky nucleophile, like this. This is 1, 2, 3, 4. This is T-butoxide. Here's the O minus, right? It's still negatively charged, but it's a little tougher for it to come in here. So when you have T-butoxide or any big bulky nucleophile, and you have a primary, it does something else. Let's talk about what it does. So it's just a little bit too bulky to get in like backside attack like that. So instead, it does something called E2. SN2 is dictated by sterics, by size. So you want less blocking groups and small, good nucleophiles. Potassium T-butoxide, very big. So instead what this does is it comes in, takes off the hydrogen next door to the leaving group. This flips down and that leaves. So the difference between SN2 and E2 is usually we want secondaries and tertiaries for E2. And the reason why is because if it was a primary or methyl, a lot of times it'll do SN2. So if you have a small, good nucleophile, it's also a strong base usually. So instead of forming a double bond, it could come in as a nucleophile. But if you have a secondary, it's less likely to come in as a nucleophile and more likely to come next door and take off a hydrogen because it's more blocked. Does that make sense?
Yeah.
Okay. Okay, and if it's a big blocking group like this or big nucleophile like this and strong base, that also indicates that it's going to be E2. It's just too big to get in there. Okay. What was I going to say? Okay, so a couple other things to notice about E2. Number one, it always takes the hydrogen off next door to the carbon with the leaving group. There's a lot of minor details about all these, but this is kind of the main idea. We can talk about more stable double bonds and anti-coplanar and all that stuff, but this is kind of the main idea. Let's do the last one. E1 starts the same exact way as SN1. So let's go back to our tertiary here. and the leaving group just leaves,
Mhm.
right? So maybe thinking, well, if it starts the same exact way as SM1, how do I know if it's going to be SM1 or E1? And the fact is, you get both at the same time. They always happen at the same time. Now, the difference is SM1 is usually favored over E1 unless you have high temperatures, and then it switches. So it's like major and minor, and they switch
Okay.
at high temperatures. But here's the difference. At this step, instead of the nucleophile coming in, which is water,
Mhm.
water is a weak nucleophile, but it's also a weak base. It's going to come in, grab this hydrogen, and that flips down to a double bond. Does that make sense?
Yeah.
So the water's doing something different at this step. Instead of being used as a nucleophile, instead of being attached onto the carbon, it's being used as a base. Your final product would be so those are the main mechanisms.
Mhm.
Okay. These kind of show up throughout the course.
Mhm.
There's variations of these. Like when we start talking about like stuff like this. Like you can see how it's a variation of all these four. Okay. There's a lot more mechanisms we can do. What do you want to start with? Is there a certain chapter you want to?
Chapter 12 in my book is probably the most like reaction heavy, and it's alkene chemistry. Hydroboration is one I'm like pretty okay on, the one that makes like the triangle with the I think that's what I'm thinking of.
Are you thinking of
Or-
oxymercuration, demercuration, or are you thinking of adding? You mean halogenation, like Br2?
Oh
that
yeah,
triangle?
yeah, that one. I'm pretty like fine with the mechanism on that one. Let me make sure.
Do you want to go over oxymercuration, demercuration?
Sure. Yeah, that one's is a lot of stuff.
Okay. Let's start with that.
Okay.
So, actually, before we go over that one, let's go over this one. Let's go over we'll kind of ease our way in there.
Okay.
So, let's use. Let's see what happens here. Now, before we go over this, have we talked about carbocation rearrangement?
Yeah.
Okay, so that's something else I'll go over too.
Okay.
Alright, so the first step you should do in any of these mechanism problems is think about what's going to happen first. Well, I have an acid. Anytime you have an acid, or if they say H plus, or if they say HA, or acid, or whatever, anything that indicates an acid, that's the first thing you do. You're going to protonate something.
Mm-hmm.
So, what here can get protonated?
Double bond.
Exactly. From now on, think of a pi bond as a Lewis base. It wants to go after something positive.
Mm-hmm.
Either H plus or Br plus or Hg plus or anything plus. So, now, here's where you gotta be careful. And some teachers are very particular about this. If you mix together H2SO4 and H2O, you no longer have H2SO4. These two react to form hydronium. Do you remember this from Gen
Yeah.
Chem? Like, this is, so, by the way, let me back up. What kind of acid is this?
What do you mean?
Strong or weak?
Strong.
It's strong. That's what I was telling you about. Like, as soon as you mix this with water, it's going to
Mhm.
fully react with the water. And then one of these H's is going to go into the water to form hydronium. So when you write the mechanism, I would start with hydronium, not with sulfuric acid, because there is no sulfuric acid left.
Okay.
Does that make any sense?
Yeah.
Okay. Some teachers will take off like a point if you don't do that. So I'm just trying to see
Yeah.
how it. Yeah. All right. So first thing is, like you said, this gets protonated. So this is the Lewis space. It grabs the H plus, and this pops off as water. So then we get this. Now, before we do anything else, we should think about where the H goes and where the positive goes.
The positive will go like where there's more carbon, so right there.
Right there. Very good. I'm going to put the H on here, which means we put the positive there. Now, whenever you make a carbocation, and from now on until the end of your chemical career, you need to stop. It's like a stop sign. And look to the left, look to the right, look all around to see if that positive would be more stable anywhere else.
If it moves over.
Yes. So this is the tertiary, this would be secondary. Oh, okay. So I need to put that somehow over here. Now, let's see what we can move. Well, we have a CH3 here. We have a CH3 there. And there's also an H right there. It's not written, but it's there. If you have a choice to what you're going to move, either a hydride or a methyl, you use the hydride. Pick the smaller one first. It's easier to move a hydride than it is a big methyl. So that's what's going to happen. It's called a 1,2 hydride shift. This is going to shift over to that spot.
So when I'm writing the mechanism, I can just do like an arrow. I don't have to say like I'm doing a carbocation rearrangement. Like they just know.
They just
Okay.
know. Exactly. And they know by where you put the positive to. So this guy had a hydrogen and there's a methyl here. Once you've shipped that hydride over, now it looks like this. And the positive is where?
On the left.
Very good. So watch out for these. These come up all the time. And now it's like an SN line.
Oh, okay.
Okay, because now, once you take that off, what are you left with here?
Water.
Water. And there's also a lot of water in there too. Water is the only thing in the solution that can be a nucleophile, right? Because positive things don't attract positive things, but water is attracted there. We saw that with the SN1. Water has a partial negative side on the oxygen side. You don't have to write the partial negative side. I was just trying to show you. So that's going to come in right on that carbon right there. Just like SN1 though, this is a flat molecule right here. It's going to come in top and bottom, which means if you have to worry about stereochemistry, make sure you show both.
Okay.
This is not a chirocarbon anyway, because these are the same thing. But if it was, then if they asked you to show it.
Okay.
Okay. And then the last step is almost always the same. You take the extra H out. Yeah. I'm sure you can do that.
Okay.
Okay, so let's go over what happened here. So what happened was we got rid of the pi bond, broke the pi bond, and added H and OH. But the weird thing is we added H and OH in kind of weird spots. It's only because the carbocation rearrangement. Now, let's say I didn't want the carbocation rearrangement. Let's say I wanted to put OH on this carbon right there. Have you talked about Markovnikov and anti-Markovnikov?
Yeah.
Okay. So if I wanted to put OH right there and H right there, would that be Markovnikov or anti-Markovnikov?
Markovnikov.
It would, exactly. So, well, I can't use H plus and H2O because I wouldn't get that, right? This is what I got from that. So let's try something else. Let's try the oxymercuration demercuration.
Okay.
So, you use oxymercuration demercuration when you want Markovnikov, H and OH with no carbocation rearrangement. That's the advantage of using this. So, let's start this off. Now, this is what you're going to see. You're going to see, like, do you guys use OAC2 like that? Or what do you guys use as this? Is that how it's written in there?
I can't remember how
I
it's
just want to keep it.
I think it, that looks familiar. I don't know if my last teacher might have done that or...
So it just means you guys actually draw out the acetates, it looks like. Yeah. Okay, it means acetate.
Okay.
So this is the abbreviation for acetate. So it looks like in the book they actually write out the whole thing, like O. It's just acetates.
Okay.
There's 2 of them. So there's another one on the other side. All right, but let me show you the abbreviation if you want to. So usually you put like Hg, OAC2, and H2O as a first step, and the second step NaBH4 and OH minus. Okay, well, let's go through the mechanism. This is probably what you're going to see, something similar to this, like overall reagents. Okay. First is this. This is mercury 2 acetate. Okay, so each acetate has a -1 charge. What does the mercury?
+2.
Yes, exactly. Now we talked about pi bonds. Pi bonds are attracted to positive things. They're a Lewis space. So before anything else happens, one of these acetates washes away into the water. Acetates, by the way, are really soluble in water anyway. So, aha! Now I have something positive, right? And now this pi bond here can go after that positively charged thing, just like it went after H plus last time. Okay. So let's draw what that looks like. Always attach the positive thing to the least substituted side, just like we did with the H. Last time we put the H plus here and put the positive there. Same thing here. Put the Hg here. But here's where it gets a little bit weird with this mechanism. Have you gone through this mechanism before?
I think we did pretty quickly, so I got confused. I remember him going over it a little bit.
I just want to make sure it's in the book. Right? Yeah, it is. Okay. All right. Here's what gets a little bit weird. Mercury has its own electrons. Okay. Anything that has its own electrons can donate some of those to this other carbon here. Instead of this being a carbocation, that positive charge can be shared between these two. So it's like half positive there and half positive there. So it's one of those triangle reactions. It's similar to the bromine, but not exactly the same. Because this is only like half a bond. Okay. So the next thing is something's going to come into one of these 2 carbons. And that's why we put water right here. That's what comes in is the water. Which carbon does it want to come into? The bottom one or the top one? What do you think? The top one. It is, because that's the one with the positive charge. So nucleophiles always go after positive things. So this comes in here, and that half bond just kind of breaks off. You can kind of see how we're getting to the Markovnikov, right? Because we wanted OH right there, and that's what's going to give us our OH on that carbon. So then you get this. And the next step is the same. Something else comes in, takes the other H off. I can skip that step. We've done that a million times. Another water comes in, takes it off. You get this. And we are done with step 1. Step 1 was to use this. Now we need to get that. So that was the oxymercuration part. The oxy is where you add the oxygen on, and the mercuration is where you add the mercury on. Now we need to do the demercuration. That's step 2. Now, NaBH4, here's how you can think of this. You don't have to worry about the mechanism, because I don't think even the book goes over the mechanism. Let's see if they go over the mechanism. No, they just tell you what happens. Okay, so all you have to know is NaBH4. These hydrogens are actually hydrides. This is called sodium borohydride. So hydrides are kind of like this, with a minus charge. So it's going to come into that carbon right there, and the mercury is going to leave. All you have to know is it replaces the mercury with the hydrogen. That's the last step. So what you end up getting is Markovnikov. You got the H right here, which is this H right there, and the OH right there, with no carbocation rearrangement.
What did the OH do then in the like after the sodium borohydride?
We have to keep it under basic conditions.
Okay.
So it doesn't really do anything in the reaction. Sodium borohydride is actually a very strong base also.
Mm-hmm.
So if there's any regular water in there, or if there's anything that could react with this, it will react with this instead of this. So we have to keep it under basic conditions.
Okay.
Okay. So there are basically three ways to put H and OH on something. The first one is what we talked about, like the acid catalyzed hydration. For that one, you have to watch out for the carbocation rearrangement.
Mm-hmm.
The second is this one. You don't have to watch out for carbocation rearrangement. And there's the third one, which is the hydroboration oxidation. Do you want to go over that one too?
Sure.
Okay. Let's take the same exact example. Usually you're going to see something like BH3, THF. Have you seen this before?
Oh, yeah. Okay.
This mechanism is crazy.
Yeah. We don't have to go over this one. We went over this a lot in class.
Oh, you did? Okay.
Yeah.
All right. But the point is, I'm just going to go over the first step with you, just to give you like the point. So, believe it or not, hydrogen is actually more electronegative than boron. So these get partial negative charges, and the boron gets a partial positive charge because hydrogen is more electronegative. So remember, we said the pi bond always goes after the positive charge, or at least the partial positive charge in this case. So I know exactly where boron is going to attach. It's going to attach onto this one, which you can kind of see how anti-Markovnikov comes into play here.
Yeah, and it does it like 3 different times.
Exactly. You got it. Exactly. Okay.
I just forget the names of them, but then once you start like writing out what their reactants are.
Oh, you don't have to know the names. I just throw it out there. Let's see. Did that. Let's see. There's no mechanism for hydrogenation. You just kind of have to know those. Have we talked about carbines?
I think so. Let me see. He took out a lot of stuff since it's going so fast. We're not doing a lot of sections. It says to skip 12-9. Yeah, if that's the.
Never mind. How about epoxides?
Oh, we can go over that.
Okay.
That confuses me.
Let's go over a few ways to form epoxides, and then we'll go over how they open up. So how they form and how they open up. All right. There's 2 ways to form an epoxide. One is like this. Let's say I have a molecule like this. Okay. If I use a strong base here, even something like hydroxide, strong bases go after the easiest hydrogen to take off, the most acidic hydrogen, which is probably going to be this one, right? Attached to the So this is where it gets a little bit weird. Whenever you have a good nucleophile and a good leaving group on the same molecule, it can react with itself. Seen this before? Let me give you an example of that. Most halogens are good leaving groups except for fluorine. Fluorine's not a good leaving group. So what's going to happen is it's going to do an SN2 with itself. It's negatively charged, so it's a good nucleophile. It's going to come in and attach onto that carbon at the same time that one leaves. Same thing here. It's just shorter. This makes a 1, 2, 3, 4, 5-membered ring, like this. That's THF, by the way. So, but yeah, so this can cyclize on itself. Same thing here. It's going to come in here and do an SN2 with itself. Come in here as that leaves. SN2s all happen at the same time. Am I losing you?
No.
Okay. Okay, so then that's one way to form these epoxides.
Does it have to be under any certain like reagent, or it just says that on its own?
Well, this is only if you start with this. If you start with an alcohol and next door there's a leaving group and you use a strong base, this is what will happen. So that's usually not how we form epoxides, but it can. Here's another way we form epoxides. Starting with a double bond, and that's what this chapter is probably going to go over. We use something called peroxy acids. So do you have to know this mechanism, or do you just have to know what happens?
What section was this, did it say?
This is 1210.
Yeah.
Okay. Yep.
Oh yeah, I remember this was in our slide too. Just to make sure we know this one.
This is the mechanism right here.
Yeah.
Okay, let's go through it.
Just remember lots of arrows.
Yeah, it's like 1, 2, 3, 4 arrows at a time. So let's go through it. Let me line it up, just like they have it lined up. This is R and R. Okay. So this is a peroxy acid. A peroxy acid looks like this. I'll put it over here in a second, but I just want to show you what it looks like before we do that. The name comes from combining a peroxide and a carboxylic acid. You can kind of see that's exactly what you combine here. You can kind of almost see the carboxylic acid, but there's a peroxide in between. Okay. So, let's twist this thing around. Like, basically turn it this way. And so you get something like this. The reason why I want to twist it is because this last oxygen here before the hydrogen is the oxygen that adds across this. So I want to make this oxygen like closest to the double bond as possible. Okay, so let's go over the arrow pushing here. Here's what's going to happen, and this is your goal. Your goal is to get a regular carboxylic acid and this oxygen to add across here. Alright, so to do that, you're going to need to remove this hydrogen, right, and put it on this oxygen over here. So, in that case, we need to use this set of bonds here, because we want to end up, this is what we want to end up with. So keep that in mind. We want the regular carboxylic acid, this H on that oxygen. So we're going to need it singly bonded. So let's use this pi bond here to grab that H. And that's what makes this new bond right there. Okay? That leaves this carbon without 4 bonds. So this one's going to have to flip down. to make that double bond right there. Okay?
Mm-hmm.
Now this leaves this O kind of by itself, except for this needs to go, actually, sorry.
Well, is it now? It's kind of negative because the H is gone?
I did the wrong arrow, sorry.
Okay.
I need this one to flip into a double bond. That's what makes this. That would make this exact molecule. But you're right. What's going to happen now is what's going on with this guy? I don't know. So what happens is this this oxygen here is now electron deficient.
Mm-hmm.
If you think about it, it's still going to have these. It's still going to have these 2, 4, 6 electrons, but that's not enough. So this Lewis base can go and make a new bond with that oxygen. But at the same time, these electrons make a new bond with that carbon. The reason why is because if you make a new bond right here, that forms a carbocation. If anything here has any electrons that can make another bond on the carbon over here, instead of a carbocation, it will do it. Like bromine and mercury, in this case oxygen. Okay. So what you end up getting is that carboxylic acid we just saw and this. Now, I haven't been drawing this in, but I'm going to draw this in from now on. Whenever anything adds all at once, and there's 2 arrows like this, when it adds onto the double bond, it always makes a triangle on one side.
Mm-hmm.
So whenever you have a peroxy acid, like this, this is what happens. Now, a common peroxy acid we use is something called MCPBA. Have you heard of that before?
Yeah.
Okay. It stands for metachloroperoxybenzoic acid. It's just a peroxy acid.
Mm-hmm.
Does this make any sense?
Yeah.
Okay. Let's go over how to open up the epoxide. Have you talked about that?
Mm-hmm.
Okay. There are 2 ways to open up a peroxide. So let's go over those 2 ways. There's acid catalyzed and base catalyzed. So let's try the acid catalyzed. Let's do this. What do you guys use as a weak acid? Do you guys use NH4Cl, or do you guys use let me just keep it consistent with what you guys use. As your step 2. Okay. I'm just gonna use water. Okay. You just have to use some sort of weak acid at the end.
Mm-hmm.
Have you heard of something called an acid workup?
Mm-hmm.
Okay, that's what I'm talking about. Okay. So let's do the first one. Whenever you have an acid, what do you do first?
Protonate some more.
Protonate. Hate is going to hate, acid's going to protonate. Okay. The only thing we can protonate is the oxygen here. I think the air conditioner just turned off. Got a little warm in here. Sorry. Alright, so that's the first step. Okay. Now, this is very similar to that Br plus triangle. And you said you're good with that mechanism, right?
Mm-hmm.
Okay. Now, because it's very similar, that positive charge can actually be shared by one of these carbons. Now, which carbon here would want to share that positive charge? In other words, which carbon here is more happy with a positive charge? This one or that one? Exactly. So the positive charge is going to be shared by the secondary carbon.
Mm-hmm.
So that means when the water comes in, let's actually, I forgot something. I forgot to put the wedges in there, I'm sorry. That's important because remember we talked about SN2?
Mm-hmm.
SN2, the nucleophile, came in the opposite way to the leaving group.
Mm-hmm.
It's the same idea here. What's going to happen I have it backwards. Yeah. There we go. Yeah, like that. So what's going to happen in this case is when the water comes in, let's say this is water. Okay? And it wants to attach onto this carbon because that carbon is the partial positive charge. When it comes in though, it can't come in on top of this.
Mm-hmm.
It has to come in the other side. So the water's going to come in and make a new bond on this carbon at the same time that this breaks off.
Mm-hmm.
So notice those two are going opposite directions. And it's always the case for epoxides. Epoxides always break open going opposite.
So it's anti.
Exactly, it's anti. So the water comes in as this breaks off. But it does matter which one. Under acidic conditions, you always go on the more substituted one because that's the one with the partial positive charge.
Mm-hmm.
So you're going to end up with something like this. Once again, something else comes in and takes the extra H off. So if you need to get two OHs that are anti to each other,
Mm-hmm.
this is how you do it. You use an epoxide and you acid catalyze hydration, and you get two OHs. So basically, here would be what I'm talking about. Let's say we wanted to turn this into this.
So you do the first step would be to like make the epoxide from the double bond.
Very good. So use that MCPBA. And then in this case, it doesn't really matter which side you put it on, right? Because they're both secondary, but you can still use H plus H2O or H2SO4 and H2O or whatever.
Mm-hmm.
Let's say I wanted this. I'm kind of going off on a tangent here, but it's a good thing to go over. And if I want a syn addition of two OHs, meaning the same side. So, have you talked about the reaction with OSO4?
Yes. What's the name of that one?
Dihydroxylation.
Okay, yeah.
So,
we did that one.
So let's go over it because it's the exact opposite. It'll give you a syn addition of two OHs. So let's go over how that works. So when you have a double bond, like this, these two carbons are trigonoplanar, so this whole thing is flat.
Mm-hmm.
So what happens is, this is what OSO4 looks like. It's flat also. It's square planar.
Mm-hmm.
Okay, so it's like a ninja star or like a crab claw.
Mm-hmm.
So these two options here are gonna come in and attach right on those two carbons at the same time. So here's my double bond right here. And these two are going to come straight down and attach on the same side of that double bond. And when they do, you get something like this. You don't need to know the mechanism of this. All you have to know is that it attaches on the same side at the same time. The second step is just, this is a weak acid. Weak acids will protonate these O's basically,
Mm-hmm.
and eventually you get this. So if you want an anti-dihydroxylation, you have to go through these two steps. If you want a syn, you go through this one step. Alright, let's go back to the base, because we still haven't, that was under acidic conditions, now let's do under basic conditions. Let's go back to our example here. Do anything fun this summer?
After my summer session ends, I have like 2 weeks off of school before like fall quarter starts, and I'm going to Hawaii with my family.
Oh, that's cool.
Yeah, it's my parents' 25th anniversary, and they used to live there and got married there, so they haven't been back since then.
They haven't been back since then? 25 years?
I think my dad may have, but my mom hasn't, so they haven't gone back as a couple yet, so very excited.
That's very cool.
Yeah. Did you have a good summer?
It was okay. Can't complain. Just visited with family. I had my sister and my niece and nephew come out from Florida, so
Oh, cool.
did the usual tourist stuff.
Yeah. Lots of stuff to do here, though.
Yeah, we went to Disneyland and yeah.
They're close to Disney World, though, so.
That's the thing. Like, do you still want to go to Disneyland? Because like, yeah, they had passes to Disney World, so yeah, we are. Okay. Okay, so let's do this case. So start with the same exact thing, but now we're under basic conditions. Now, let's go over what this is. Let's go back to what we talked about before. What do you know about this? This.
It's a good nucleophile.
It is a good nucleophile. It's negatively charged. It's also a strong base,
Okay.
right? And that's why I said basic conditions. Do you want to go over what we consider a strong base, like the common strong bases?
Sure.
Okay, there's a list. It's the most common strong bases are alkoxides, like this, like methoxide, potassium T-butoxide. So even propoxide is sometimes used. So any alkoxide. Now that list does not include acetate. This is not a strong base. This is a weak base. Okay. Sometimes we use sodium hydride. Have you seen that before? Okay, that's another strong base. Many times we use this. Very, very, very common. And when you see these two right here, we only use those to be a strong base. Almost always. Okay. Let's see, what other strong base do we use? I don't know if you've ever seen these, but like lithium, you've seen
That's
this?
usually used to like add a carbon, right?
It's they're good nucleophiles because once again, anything negatively charged is a good nucleophile. So if you have something like this, yeah, that carbon's a great nucleophile because it's negatively charged, but it's also a strong base, so you have to watch out for that too. So some of these reactions you have to be careful because those can be used as strong bases too. And those are the most common I can think of, other than ones you already know, like potassium hydroxide, lithium hydroxide. Okay. All right, so what we know about that is it's a strong base and a good nucleophile. Well, there's no H's that can be taken off here, really. So it's going to come as a nucleophile. But here's where it's a little bit different. When we talked about SN2, what dictated how it comes onto the carbon? In other words, which carbon do you think it'll go onto? This one or that one?
That one.
Yes, because SN2 is dictated by sterics, by less blocking groups here. So in this case, it'll just go to whichever one's easier to get at, just like
Mhm.
SN2. It's kind of the same because SN2 is a good nucleophile, right? So it's going to come into this one instead, attach, as this breaks off.
Okay.
You still get anti, but you get this attaching to the less substituted carbon.
Okay.
So in this case, this attaches onto this carbon as that breaks up, which gets you still anti. And that's why I say step 2 is adding water, because we need a protonate. Use some sort of mild acid basically to protonate that O. You might see it as water, or you might see it as H3O plus, or something to put an H onto that is step 2. So you'll end up with this. Okay. This NaOCH3 could have also been hydroxide.
Okay.
Then, once again, this would come on, this would be H, and it would come in there, same idea.
So it's another way to get to anti. Like, if it was NaOH, it's this kind of the same as with the acid, right?
Yep, exactly.
It's the same thing. Okay.
Exactly. We have a few minutes left.
Okay.
Unless you want more than an hour, it's up to you. Any last minute? Chapter 12 or... Looks like you go over HBr and ROR.
Mm-hmm.
And you talk about... so that's a mechanism. Do you have to know those radical mechanisms or no?
I think so. Is ROR written as something differently, or is it always written as that? Because I remember seeing it last quarter like that, but I...
Like ROOR. It just means a peroxide. That's all it means.
Okay.
So yeah, sometimes we write it like this. Or you might see it like says like peroxides,
Mhm.
or you know what I'm talking about? Let me look at how they write it in the book. Yeah, they use it as ROR, R-O-O-R.
Okay.
Okay, do you want to go through this mechanism?
Sure.
Okay. There are two anti-Markovnikovs that add across a double bond that you need to know. One is the hydroboration. We talked about that one. This is the other one. So, which one do you want me to use?
ROR is fine.
Okay.
I just couldn't remember.
Okay. Here's what we know about the OO bond. Very weak bond.
Mhm.
Okay, so it's so weak that it can just break right in half. So notice when I did these arrows, I did a single-headed arrow,
Mhm.
which means one electron. Okay. So that's what you get first. You get this. That's just to start the radical process, like to make radicals. So we're also using HBr. So let's see what happens when this comes in contact with the HBr. This is a very unstable radical. Radicals are unstable.
Mhm.
This would much rather be an alcohol. So what it does is it grabs an H from the HBr, so it can become an alcohol. But it only needs one more electron. So it's going to take one of these electrons, and that one electron,
Mhm.
and the other electron goes on to the Br, and you get this. these two steps are actually considered both the initiation steps, because the point was to somehow get to BR dot. And then once we get to BR dot, it's going to go into the propagation steps, which is like the cycle that happens. So, alright. So this was to start the radicals and then to make a BR dot radical. But now that we have the BR dot radical, let's go over what happens. Let's take this example. Okay. So this bromine is electron deficient, only has 7 electrons. So kind of the same idea as last time. Pi bonds want to go after things that are electron deficient. Positive things, partial positive things, anything. So, but it only needs 1 more electron. So I'm going to split up these 2 electrons. I'm going to use 1 electron and this 1 electron to make a new bond. But the other electron has to go either on this carbon or that carbon. Now, radical stability follows the same trend as carbocation stability. So, which one is a more stable radical? This one? Exactly. So this extra electron here is going to go onto the top there. And you end up getting this. You could kind of already see it's anti-Markovnikov, right? So, okay. But we're not done because they're supposed to add H and Br. So let's do the next propagation step. So these are initiation, just in case you have to label them. And these 2 are propagation. Propagation means a cycle, like it keeps going and going. It's going to need an H from something. Well, might as well use another HBr. So let's use an HBr here. So this 1 electron and 1 of these electrons, we're going to form a new bond between that carbon and hydrogen. And the other electron that was in this bond is going to go onto bromine. So no more radical, and the hydrogen's on there. You can draw it on there if you want. Now, there's a couple reasons we call this a propagation. Well, these 2 propagation. One reason is, notice how we used the BR dot and then we regenerated it. And this can go back to the start, find another one of these, and start the whole process over again.
Okay.
So you can kind of see the cycle here.
Yeah.
Also, if you were to cross off everything that's the same on both sides, like BR dot with BR dot, and this dot with that dot, you would get your overall reaction. It would be this plus HBr goes to this.
Okay.
So those are 2 ways to kind of check your propagation steps. Last is a termination step, but do you have to know the termination step?
I don't remember doing anything with the... Is it to get rid of the BR dot?
Exactly.
I don't think I remember.
No, it looks like you don't have to. Okay. So overall, this is your final product, which means it's anti-Markovnikov. How are you doing?
Good. Okay. This is making more sense.
That's good.
Yeah.
Okay.
I just never know like what to do first, and like it just overwhelms me. When I like just see a reaction, I don't know what I should do, but it's making a lot more sense this quarter than it did last quarter, which is good.
Very good. Yeah, so a couple suggestions on that is, like I said, if you see an acid, that's the first thing you always do when you're probing something. Other than that, it's kind of it's a lot of memorization, which reagent does what. So, but you can kind of reason your way through the problem too at the same time. Like we talked about, pi bonds go after positive things or electron deficient things. They always attach onto the carbon that's resubstituted, so on and so on.